All right, guys, so in this last little segment of your summer work, we're going to be looking at fluid dynamics, getting a little bit of introduction to fluid flow. Now, you've noticed that in everything we've done so far, we've been looking at fluid statics, right? Where the fluid was at a rest. Things were sitting inside of a container. Things were floating on top of the fluid that was at rest. All the situations, in fact, in one of them I even talked about if the fluid was moving through the pipe, it would be a completely different situation. So we're going to start looking at that today. We're not going to go super in depth into it, but I want to introduce you to some of the basic introductory ideas. All right. So first thing we want to talk about is that there are basically two types of fluids that can be considered. The first one is what's called a steady state. Sometimes this leads into, in engineering, something that we call laminar flow. But a steady or laminar flow is one like the top one up here. You can see in part A where the fluid is moving in straight lines, right? It's not really bouncing around. It's not going in circles. There's no eddies there. It's just going very, very steady. Now, this often happens if there are no large obstructions, if it's not moving too fast. That's situation A. Situation B is what we call turbulent. Now, turbulent flow happens when there are large obstructions. You can see in the second kind of image of the wing has been tilted a little bit more, so it's hitting more surface area. That's kind of a larger obstruction to the air there. And that's causing, behind it, some turbulent motion. The fluid isn't moving in this nice streamline anymore. It's actually moving in more turbulent motion, and it's mixing, and actually you're creating different pressures there, and a lot of different things are happening. So most of the time in this course, when we're looking at fluids moving, we're going to be looking at steady state or this kind of laminar fluid flow. We're not going to be looking at turbulent situations. One of the things that one of the words that you're going to hear every once in a while is viscosity. Now, sometimes you hear people refer to viscosity as kind of the thickness of the fluid. You would say, for example, maybe that honey would be a good situation that would be more viscous than water. If you were to drop a marble into the honey, it would probably sink slowly, whereas when you drop in the water, it just kind of drops down to the bottom. So viscosity officially is the degree of internal friction in the fluid. So how much friction is being created inside of the fluid itself. All right, so that hopefully is something that kind of makes sense. You can think of it in some ways as the thickness. Something that's thicker probably has a higher viscosity, but we usually use that term which directly correlates to the friction there. All right, so that'll hopefully give you a little bit of a start in thinking about different types of fluids and what we're going to be looking at here. One last thing that I do want you to look at here in the top one is, when the wing is tilted up like this, you can see how some of the air is being pushed down. Okay, that's actually going to create a high pressure area down here. Now on the top, some of the air is moving up, but you can tell that in this space, there's a lot less air than there normally is. That means you got a low pressure area here. What happens when you got a high pressure and low pressure? Well, the high pushes up towards the low. All right. And so in this turbulent, because of the way the wing is placed, you're getting the wing being pushed upwards from high pressure to low pressure. So, a lot of times how an airplane flies is oversimplified and it's explained, well, this is how it is. Well, there's a lot of ways, a lot of different pieces of physics that go into how an airplane flies. So anyway, that's just another piece of it. We've talked about some of it before, but that's another piece. Let's go on to the next slide. We're going to go ahead and talk a little bit more about ideal fluids. If you've taken chemistry, you've probably talked a little bit before about an ideal gas, right? There were certain conditions that had to be met for an ideal gas. If you haven't done that, don't worry. Gases are going to come up in our next unit. We're going to talk a little bit more about ideal gas laws and things like that. That'll come up when we do thermodynamics. For now, we're just talking about fluids in general. Remember, gases are fluids, but we want to talk about an ideal fluid. Now, gases actually don't make very good ideal fluids because there are several conditions that we want to meet in order for a fluid to be considered ideal. All right, so let me go ahead and put these up for you, and then we'll talk about each one. So here's the four main conditions that we're going to be thinking about. The first one is non-viscous. Remember, we talked about viscosity just a moment ago, and viscosity was the friction inside of the fluid. So we're going to be saying that an ideal fluid is non-viscous, which means that it won't be losing any energy due to internal friction. There won't be any inside friction. We're going to simplify things here, non-viscous. Just like when we did things in the air, we often said that the air was no air friction, right? That there was nothing, no energy lost as something was flying through the air. So same thing here. The next one is steady. Now, steady just means that at a certain location, if you were to chop your pipe in half, that the velocity of the fluid everywhere is the same. Now, this is a little bit different than what you may consider if you go into fluid mechanics and engineering. In that case, you may consider that fluids at different places along your pipe are different. But here we're going to just consider that all fluids in this line are going to be the same. Now, that's not the same as you go through a pipe from a wide place to a narrow place, like what you see over here on the side. But for a given section, if I were just to draw a straight line right there, all the velocities in this area should be the same. That's what steady means, all right? Third is incompressible. Incompressible means that no matter what the pressure is, we're not changing the density of the fluid. Now, this is important because of one of the other assumptions that we're going to be making later, which is, I guess, based off of this, that the fluid is incompressible, that you're not changing the density of the fluid as we go. Now, this is the reason why gas doesn't really make a very good ideal fluid, because gases are really easy to compress and expand. So most of the time when we're dealing with ideal fluids, we're talking about liquids here, but you may be given a situation where you have gases and it may say initially assume the gas to be an ideal fluid. So pay attention for that. That means incompressible. The last thing is something, again, just to kind of simplify things so we don't have to worry about it. It is irrotational. Now, what that means is that it's not turbulent. Remember in the picture in the previous slide, go back if you need to, you saw that some of the directions of the current started to kind of loop around and create eddies. We're also assuming that it's not rotating this way around the inside of the pipe. So irrotational, meaning that none of the energy is going to rotational energy. Remember how much you loved that at the end of last year. So yes, we are simplifying, saying that there is no rotational energy here. All of the energy is going to remain constant because no inside friction, steady state, incompressible, or rotational. So this is going to simplify a lot of things for us, basically saying energy is conserved and that type of thing. All right, so hopefully that makes a little bit of sense. One of the quantities that we're going to be using a lot is something called the volumetric flow rate. Now, the volumetric flow rate we often show with a Q. Please don't ask me why. I have no idea why it's a Q. There might be a good reason, or there might not. I don't know. Q is the volumetric flow rate. Now, what volumetric flow rate is volume over time. So how much volume is going through a specific plane or a specific space in a certain amount of time. In my drawing down here, I drew this already, this line. So how much volume is going to pass that line in a certain amount of time? That's your volumetric flow rate, okay? Now, this is not in your formula packet because it's a definition. You need to know this. Just like some of the things like velocity and acceleration aren't always in your formula packet. If it's a definition, you just need to know what it is. So volumetric flow rate is volume over time. Now, really what should always be constant is something called the mass flow rate, but if it's incompressible, meaning that the density doesn't change, then if the mass stays constant, the density stays constant, then the volume must also be a constant, all right? And so we are going to mostly focus on volumetric flow rate, though understand that the real principle here is that the mass flow rate must be constant. We're just trying to simplify things and really get you introduced to the idea of fluids. If you go into mechanical or chemical engineering or something like that, you're going to spend a whole semester studying fluid mechanics and add in some calculus and some really cool stuff with it. But for now, we're trying to keep it pretty straightforward and simple. Just get the principles down. All right, you'll find that it can be pretty complex as it is, so let's not make it any worse than it needs to be. All right, so let's consider this. Let's take a pipe. So I'm drawing my pipe here. So here's my pipe. My pipe has a very specific cross-sectional area, right? Now, if that area is traveling with a very specific speed, then in a certain amount of time, it will go through a very specific distance. So it'll be able to go through a specific distance in a given amount of time based off of its speed. Now notice that my pipe here has constant width, and so it has a constant cross-sectional area. So if it's incompressible, if the density is staying the same, then what I'm going to get is I'm going to get that this volume here will pass through a specific point in a given amount of time. So that's a way of kind of visualizing this idea of the volumetric flow rate. We know that volume is equal to area times distance, right? The cross-sectional area times the distance. Now, if we want to turn that into the volumetric flow rate, we just divide by time, which means that we can get the volumetric flow rate in a couple of different ways, right? We can say that the volumetric flow rate is equal to the area times the distance, which is the volume over the time, but we can also say it this way. We can do area times distance over time, which is velocity. Now, some of you probably already knew that from our previous discussions, but this is an important idea in recognizing that if the volumetric flow rate is constant, then the A times V needs to be constant. Now, this is going to become important when we start to look at situations like the one in the bottom right-hand corner here, and what's happening is that the cross-sectional area is changing. If the cross-sectional area is changing, but the volumetric flow rate is staying the same, that means that you need to push that stuff through a lot faster because you have a smaller area to fit it through, but you got to fit through the same amount of stuff as before. Okay? And so as your area gets smaller, the velocity is going to have to increase, or vice versa. All right? We're going to look at some examples of that here in just a few minutes. All right? So that's an introduction there to ideal fluids. So here's an example. What area must a heating duct have if air moving 3 meters a second along it can replenish the air every 15 minutes in a room with a volume of 300 meters cubed? All right, so we've got a heating duct. We need the area. We don't know what shape it is. That's fine. Not going to be a big deal here. What are we noticing? Well, we notice that we have a volume that needs to be replenished every 15 minutes. All right, so that means every 15 minutes I need 300 meters cubed over 15 minutes. Now notice that's a volume over a time. That is a volumetric flow rate. So what we need is that volume to come into the room every 15 minutes. That will allow all the air in the room to be replenished. Now, this should kind of touch home because that was one of the big things during COVID-19, right? Is that you wanted the air to be able to come in and out. And that's one of the reasons why you left the windows open, because that allowed for a larger volumetric flow rate than if you just were running the ACs. The ACs would allow a certain amount of air to come in and out, but windows open would allow more. And so that allows for a higher volumetric flow rate, which allows that volume of air in the room to be replaced much more rapidly. All right, so let's go ahead and have a look at this. So we've got that 300 meters cubed for 15 minutes. I do want it in SI units, so I'm going to turn that minutes into seconds. And when I do that, I'm going to get 300 meters cubed over 900 seconds. I just multiplied the minutes by 60 to get the number of seconds, and I divide that, and I get 0.33 meters cubed per second. SI units, that is my volumetric flow rate. That's the volumetric flow rate that I need. Now, in this situation, it's asking what area must the heating duct have if it wants to move the air at 3 meters a second. Well, remember in our previous slide, we also said that Q is equal to AV. So if we know that the Q needs to be 0.33, and we know that the volume needs to be 3, and everything's in SI units, we should then be able to solve. So we're going to go 0.33. I'm going to go ahead and use the 0.33 continuing because that's what my calculator gave me. That's going to be equal to the area times the volume. Because it is all in SI units, I can go ahead and divide that by 3, and I get 0.11 meters squared. Now that's not that big. If you think about the size of the windows at school, again going to that, those windows are pretty big. It's about 1 meter tall, 1/2 meter wide, so that's about 1/2 meter squared. So you can tell by opening 2 or 3 windows, we're going to be decreasing the amount of time, because by increasing the area through which the air can flow means that with the same velocity of flow, we get a higher volumetric flow rate. And so with a higher volumetric flow rate, this can happen much, much, much quicker. All right, so there you go, a little bit of application to what most of you have lived through in the last recent history. Okay, let's move on. Example number 11, a garden hose has an unobstructed opening with a cross-sectional area of 2.85 times 10 to the negative 4th meter squared, from which water fills a bucket in 30 seconds. The volume of the bucket is 8 times 10 to the negative 3rd meters cubed. Find the speed of the water that leaves the hose through the unobstructed opening and an unobstructed opening with half the radius of the opening. All right, so here we go. Let's look at A first. Find the speed of the water that leads the hose through the unobstructed opening. So what we see is that we know that the cross-sectional area of the hose is 2.85 times 10 to the negative 4th. Okay, we know the volume of the bucket, and we know the amount of time it takes to fill the bucket. So we can actually already get the volumetric flow rate, right? That's volume over time. We know that we need 8 times 10 to the negative 3rd meters cubed. We need that much volume in 30 seconds. And so we can solve there for our volumetric flow rate. Then I got 2.66 repeating times 10 to the negative 4th meters cubed per second. All right, now the question's actually asking for the speed. Okay, well, to get the speed, remember volumetric flow rate is also equal to the cross-sectional area times the speed of the liquid. So the cross-sectional area was given to me here, which is 2.85 times 10 to the negative 4th meters squared. So we can go ahead and put that in. We'll go ahead and just rewrite this as 2.66 repeating times 10 to the negative 4th equals cross-sectional area of 2.85 times 10 to the negative 4th. Please do make sure everything's in SI units. If it's not, then you'll need to do some conversions and get it into SI. That way you don't have to worry about the units as you go. Now, if I take that 2.66 times 10 to the negative 4th and I divide by 2.85 times 10 to the negative 4th, I should get the velocity, which I get to be about 0.94. meters per second. There we go. Not too bad. Okay, so we got the speed that it leaves the hose through. Now the question in letter B is what happens if we obstruct the opening with half radius? And you've seen this before. You know, you have the end of your hose, and at the end of the hose they have something on there like this that kind of narrows it down, and so you now have a cross-sectional area that has half the radius of what it was before. That's what we're looking at. Now, there's a couple of different ways you can go about this, okay? Now, we recognize that the volumetric flow rate has to be the same, okay? So you could just take your cross-sectional area, which is 2.85 times 10 to the negative 4th, and you could go, well, I know that area equals pi r squared. You could solve for the original radius. Then you could half that, solve for the new radius, plug that in, get a new area, and then once again use the volumetric flow rate equals area times velocity with your new cross-sectional area, and you should be able to solve for your new velocity. Now it's narrower, we expect it to be going faster. That's what happens when you put that nozzle on the end, right? Is that the water goes faster, it goes further, sprays further. Well, that makes sense because it's traveling faster. Now, of course, if you're starting to really think about this, you're recognizing, well, if the Q before is equal to the Q after, that means that area 1 velocity 1 should equal area 2 velocity 2. Now, what happens to the area when I half the radius? Well, if we look at this, if the radius is half, it's being squared, that means that the area is going to be 1/4 of what it was before. So if my area goes down by a ratio of 1/4, that means that the velocity should go up by a factor of 4. So we just multiply by 4 and we get that our velocity for letter B, when it's obstructed, we get 3.74 meters per second. And I use the full number, so don't worry too much if you multiply 0.94 by 4 and you don't get exactly 3.74. I actually multiplied by the original number with all the digits there. Now, go ahead if you'd like, see if you can get that using the other process. This is something that you're going to want to be able to get comfortable with. This is a very, very common multiple choice question, which means that you want to learn how to deal with it just by looking at ratios and how are things changing and not have to worry about doing all the mathematics. A little bit of a concept test here for you. Don't get fooled. In the previous scenario, we considered the speed of the water due to a larger opening, right? And in the larger opening, it was slower. And then we had a smaller opening where it went faster. In which situation is it going to fill the bucket faster? Go ahead and pause the video, come up with an answer, justify your answer, and then check my answer. Okay, pause. All right, so hopefully you said this one. Both are the same. Now, that should make sense because we said our one assumption during that problem was that the volumetric flow rate was the same, which means we get the same volume in the same amount of time. That's how we calculated the speeds and all those other things, was assuming that the volume was the same. So in both situations, you're going to have exactly the same amount of volume coming out in the same amount of time, which means it will take exactly the same amount of time to fill up the two buckets. All right, let's try another one. Concept test number 8. Water flows from left to right in the diagram below. Identify which areas the speed increases, decreases, and remains steady. Consider the fluid as ideal. All right, so once again, find your answers, justify your answers. Don't just choose a letter, justify your answers, and then when I give you the right answer in a second, you can go back and change your answer. That's an important part of the process, all right? So go ahead and pause the video now. All right, so hopefully you recognize that as long as the radius is staying constant, the speed should stay the same. So in A, it's staying the same. From here to here, in C, it's staying the same. And from here to here, in E, the speed is staying the same. So the speed should be constant in each of those sections. So A, C, and E. So that leaves us with either B or D. Can't be any of the others because all the others show that it's speeding up in those areas. But remember, the volumetric flow rate needs to stay the same. So if the cross-sectional area is staying the same, remember Q equals area times V. So if the cross-sectional area is staying the same, the velocity must also stay the same. All right, so now the question is, what's happening in B and what's happening in D? Well, in B, you can see that your area is decreasing. So if my area decreases, if this goes down, in order to maintain the same volumetric flow rate, the velocity must go up. So in section B, we need an increase. That looks like this guy right here. But let's go ahead and check D just to be sure. So D, notice that we're going from a small area to a large area. When that happens, then the area will be increasing. That means in order for Q to stay the same, the velocity must decrease. And so velocity decrease, that's what we see right here in D, and that answers the question. All right, this idea that we've been using is called continuity. We often refer to that AV equals AV, A1 V1 equals A2 V2 as the continuity equation. Basically, it's just saying that we have to have a continuous flow rate, whether it be volumetric or mass, in this case, where those are both going to be the same. That idea of continuity is a really big idea, and you're almost guaranteed to have at least one multiple choice question that deals with this, and possibly some free response as well. But definitely look for it. You're going to see it. You're going to see it in the practice that you're going to go do right now. That's your introduction to fluid motion, and we will dig way deeper into this type of stuff when you come into class very, very soon. See you then.